Hello everyone. In this video, we will discuss how to measure the setup and hold time of a flop. Before we go into these details, let's do a quick review of setup and hold time and other timing parameters. First, the setup time. Setup time is the minimum required time duration that the input data must be stable before the active edge of the clock. Or in other words, the input D in the flip-flop must be stable before the active edge of the clock for at least setup time. This is a critical timing requirement in order to avoid possible data contention in the flip-flop. Now about hold time. Hold time is the minimum required time duration that the input data must be stable after the active edge of the clock. Or in other words, the input must be stable after the active edge of the clock for at least hold time. If this timing requirement is not met, it would cause metastability in the flip-flop. In this figure, the time shown in the blue arrow line is the setup time. The input data D must be stable for this much time before the active edge of the clock. The hold time is shown in the green arrow line, and it is the time after the active edge of the clock when the data must be stable. Another important parameter in setup and hold measurement is the clock to Q delay. Clock to Q delay is the time it takes for the flip-flop output Q to be stable to a new state after the active edge of the clock occurs. We measure clock to Q delay from 50% threshold of the clock transition to 50% of Q transition to the new state. Now let's discuss how to measure setup time in simulation. In order to find setup time, we first compute something called nominal clock to Q delay of the flop. To calculate nominal clock to Q delay, make sure data transitions from 0 to 1 at an infinite setup time or well before the active edge of the clock. We then measure clock to Q delay from 50% of the clock to 50% of Q. Once nominal clock to Q delay is computed, we keep moving the data D closer to the active edge of the clock. And subsequently, we measure clock to Q delay for each shifted version of input D. We then find the shifted version of input D where the clock to Q degrades by 10%, or in simple word, where the clock to Q is increased by 10% compared to the nominal delay. The difference of transition time between 50% of input D to 50% of the clock active edge is the setup time of the flop. When we measure setup time, we keep the hold time infinite, which means that we hold the data stable after the active edge of the clock for a long time. Now, how do we measure hold time? First, make sure data transitions at an infinite hold time after the active edge of the clock. In this figure, the transition is shown from 1 to 0 for data. We then compute clock to Q delay from 50% of the clock to 50% of Q and consider it as nominal clock to Q delay. Similar to the setup time measurement, we keep bringing the data D closer to the active edge of the clock and subsequently calculate clock to Q delay for each input D and keep checking for the 10% increase in clock to Q delay compared to nominal delay. When we reach that point, the difference of transition time between 50% of input to 50% of the clock edge is the hold time of the flop. This figure shows a graphical representation of the setup and hold time measurement. This is nominal clock to Q delay. As we move data closer to the active edge of the clock, we look for the point where clock to Q is degraded by 10%. and that's the setup time. In same way, we measure the hold time. For accurate timing results, setup and hold time should be characterized separately for a rising D input and a falling D input. An important thing to understand is why do we see an increase in clock to Q delay when we move data closer to the clock edge. As the data transitions closer and closer to the active edge of the clock, at a certain point, the setup time is violated for the flip-flop and it goes in a metastable state. In this case, output Q takes a longer time to resolve or settle to new state. This is the reason why clock to Q delay is increased. Another interesting aspect is how much degradation should be accounted for to measure setup and hold time, whether it should be 5% or 10%. The answer to this is tricky. If you pick a small percentage, you get very conservative setup and hold times, which limit the maximum clock rate of the design. On the other hand, if you choose a large percentage, there is a high risk of introducing more timing failures, which sometimes can result into silicon failures, which are harder to fix. That's all for this video. Thank you for watching.